Hello everyone. In this lecture, we are just going to discuss about the GPIO configuration of our microcontroller ATMEGA16. Let's get started. Since our microcontroller is a 8-bit microcontroller, all the registers in our microcontroller will be only of 8 bits wide. So this is the structure of 8-bit register, and here you can see it will be having 8 values from 0 to 7, or it will be having 8 bits from 0 to 7. These 4 bits 0, 1, 2 and 3 are known as LSBs, that is least significant bits, and these 4 bits 4, 5, 6 and 7 are known as MSBs, that is most significant bits. And regarding the registers that we are going to use for GPIOs in our microcontroller is DDRX register, that is data direction register, and port X, that is the data register, and pin X, and this one is the input pin address register. So these three are the registers that we are going to use for configuring the GPIO of our ATMEGA16 microcontroller. So we will see each of these registers separately. Before that, I just want to remind you two logic gates, that is AND and OR. So in AND gate, we know the result for 0 0 inputs will be 0, 0 1 will give the output 0, 1 0 will give the output 0, and only 1 1 will give the output 1. So this is the truth table for AND gate, and this is the symbol for performing AND operation. And regarding the OR, 0 0 will give the result 0, 0 1 will give the result 1, and 1 0 will give the result 1, and 1 1 will also give the result 1. So this is the truth table for OR gate, and this is the symbol for executing or performing OR in our program. So we will be using most oftenly these two operations for setting and clearing the bits in the registers. So that's why I am reminding these two gates to you. So the first register is DDRX, data direction register of the ATMEGA16. So this register is a 8-bit register used for configuring the direction of the pin for a corresponding port. That is, this register is used for configuring the corresponding pin of the microcontroller as input or output. And this X is indicating that this variable is not a constant and it will be varying depending on the port that we are configuring. That is, we have 4 ports in our microcontroller: port A, port B, port C and port D. So we will be having 4 different data direction registers for each ports, such as DDRA, DDRB, DDRC and DDRD. So these are the individual bits of the DDRA register, and these are for DDRB register, and these are for DDRC register, and these are the individual bits of DDRD register. This goes like this: DDA0 to DDA7, DDB0 to B7, C0 to C7 and D0 to D7. And let's understand how we can configure the pin as input or output using the DDR register. That is, if you are writing 0 to a particular bit in DDRX register, that particular bit or that particular pin will be configured as input, and if you are writing 1 to the corresponding pin, that will configure the pin as output. So let's understand this. There are two methods for setting or clearing bits in a register. First one is individual bits method, and second one is 8 bits data method. So this individual bits method is used whenever we just want to set 1 or 2 bits of the register and we want to leave the other bits of the registers undisturbed. We will use this 8 bits data method for setting all the bits of the corresponding register. So these are the difference between these two methods, and we will see the individual bits method for setting or clearing the bits in DDRX register. So initially, now we know that if we write 1 to the pin, that will configure the corresponding bit as output, and if we write 0, it will configure the pin as input. So let's take the DDRB register, that is, we are just going to configure the port B. If you are going to configure any other port, you just want to take the corresponding DD, RC, RD, RA registers. So now how can I make this DDB0 bit as output? For that, I just want to write 1 to the DDB0 bit, right? So that can be done by using this line. You can see this line will set the DDB0 bit of DDRB register. That is DDRB equal to DDRB R of 1 left shift of DDB0. So let's understand this line. Initially, let's assume all the bits in the DDRB register is 0. And this 1 left shift of DDB0 is nothing but a 8-bit value that will set to the 0th bit of the 8-bit register. So its value will be 00000001. So when I perform OR operation of these two registers, you can see 00 will give me 0, 00 will give me 0, and only this 01 will give me the result 1. And the result we are storing in the DDRB register. So now the value of DDRB register is 00000001. So now you can see this DDB0 bit is set and it is configured as output. So this is how you can set a bit in a register and you can configure the pin as output in DDRX register. And similarly, this expression can be shortened like this. That is, instead of writing DDRB equal to DDRB R of 1 left shift of DDB0, you can write DDRB R equal to 1 left shift of DDB0. Both are having the same meaning. So you can neglect this DDRB written again. Similarly, if I want this DDB1 bit also configured as output, I can just write DDRB R equal to 1 left shift of DDB0 and then R of 1 left shift of DDB1. So this line will set DDB0 and DDB1 bits of DDRB register, configuring these two pins as output. Like this, you can perform as many OR operations in a single line as possible. And if I want to make all these 4 bits from DDB0 to DDB3 as output, I can write DDRB R equal to 1 left shift of DDB0 R of 1 left shift of DDB1 R of 1 left shift of DDB2 R of 1 left shift of DDB3. So this line will set all the bits from DDB0 to DDB3 and we are configuring all the pins as output. And if I want to make this bit as input, we know that we just want to clear this bit. Irrespective of the current value that it is having, we just want to clear this bit without disturbing all the remaining bits in the register. So in individual bits method, we will only set or clear the corresponding bit, leaving all the bits of the register undisturbed. So that can be done by using this line. DDRB equal to DDRB ampersand of negation of 1 left shift of DDB0. So this will clear the DDB0 value irrespective of the current value available in the DDB0. Let's understand this line. Let's assume the initial value of DDRB to be 00000001. I am just purposefully assigning this value as 1 and the 1 left shift of DDB0 will give the value 00000001. And negation of this value, we will be getting all the zeros as ones and ones as zeros in this register. That is, result of this negation of 1 left shift of DDB0 will give us 11111110. And now when I perform DDRB register value with the negation of 1 left shift of DDB0 value, you can see all these values will be same as available in the DDRB register, as we are performing AND operation of that bits with 1. So any value AND of 1 will give me the same value. That is, if it is 0 here, it will give me 0 here. If it is 1, I will get 1 here. And you can see all the values that is available from 7 to 1 bits in the DDRB register is available over here. And here you can see the value is 0. So anything AND operation of 0 will give me the result 0. Whatever value that is present here will be cleared. So this is how the DDRB register will be holding the value 00000000 at the end. Thus this DDB0 value is cleared using this line. You can also simplify this line as per this. Instead of writing DDRB equal to DDRB ampersand of negation of one left shift of DDB0, you can write DDRB ampersand equal to negation of one left shift of DDB0. And similarly, if I want this bit also to be configured as input, I just want to clear this bit also. That can be done using the statement DDRB ampersand equal to negation of one left shift of DDB0 ampersand negation of one left shift of DDB1. Like this, you can perform as many AND operations in a single line for clearing bits in a 8-bit register. So if I want to make all these pins as input from DDB0 to DDB3, I just want to clear all these 4 bits. Remaining bits we will leave undisturbed. Let's see, this line will do this, right? That is DDRB ampersand equal to negation of one left shift of DDB0 and of negation of one left shift of DDB1 and of negation of one left shift of DDB2 and of negation of one left shift of DDB3. So this line will clear all the bits from DDB0 to DDB3, making that pin as input. So this is how you can set or clear the bits of the register in your ATMEGA16 microcontroller using individual bits method. And let's see the next method, that is 8-bit data setting method. So let's take an example for understanding this method also. So if I want to configure all these pins from DDB0 to DDB3 pins as input, and if I want all these pins to be configured as output, that is DDB4 to DDB7 must be configured as output. What I can do is, I just want to write 1 to it and I just want to clear all these bits, right? For that, I can provide a 8-bit binary data directly to the DDRB register. That is, I can write DDRB equal to 0B11110000. So this 0B is representing that we are providing a binary data, and these 8 bits is corresponding to the respective bits. That is, the first bit is set to the DDB7, that is the 7th bit of the register, and the next bit is set to 6th bit, and 5th, 4th, 3, 2, 1 and 0. So from the left, the bits will be set from 7th bit to 0th bit on the right. So in this order, the bits will be set. So instead of configuring 8-bit binary data to the register, we can configure equivalent hexadecimal values for this binary data. So for representing this binary data into the form of hexadecimal, we just want to change this 0B to 0x. And then we just want to split these 8 bits into 4 bits. That is, first 4 is MSB and next 4 is LSB. And then you can see this is the table for converting binary data into equivalent hexadecimal. So this 1111 in binary is represented as F in hexadecimal, and this 0000 is represented as 0 in hexadecimal. So I can write DDRB equal to 0xF0. So I can write this hexadecimal value instead of that 8-bit binary data to the DDRB register. So thus this 8-bit data method is used for setting all the 8 bits in a register of a microcontroller. So let's take another example, that is, if I want to configure DDB2, DDB4, DDB5 pins as input and all the other pins as output in DDRB register. So I just want to set these 3 values, that is the 2nd bit, 4th bit and 5th bit values as 0, and all the other bits 7, 6, 3, 1, 0 must be set as 1. As we know, 1 is for output and 0 is for input. So I can write the binary data 0B 11001011. So these zeros will set the corresponding pin as input and ones will set the corresponding pin as output. So initially we just want to configure the binary data onto the register, and then in the next step we just want to convert this data into hexadecimal using the table. So for converting that, we just want to replace the 0B with 0X, and then we just want to split the 8-bit data into 4 MSB and 4 LSB. So the MSB is 1100. So 1100 in binary is having the hexadecimal value C, and 1011 is having the hexadecimal value B. So the hexadecimal value is nothing but DDRB equal to 0xCB. So this is the equivalent hexadecimal value for the binary data available here. So thus this line will configure the 2, 4, 5 pins as input in DDRB register, and it will configure all the other pins as output. And thus this 8-bit data method is used for configuring all the bits of 8-bit register in a microcontroller. So for that, the steps are simple. I'm just brushing you through that. For that, I just want to configure the 8-bit binary data, and after that we just want to find the equivalent hexadecimal data for the binary data provided using this table, and then we just want to load the hexadecimal data to the 8-bit register. So this is the step for 8-bit data method, and we will continue in the next lecture. Thanks for watching.